This might not be your first encounter with the Ralph Wiggum Loop because it's been featured in podcasts, in videos, social media, news sites, technical articles, security blogs, training courses, GitHub, and plugins for coding tools. It all started last year with this post on a developer's blog about a software development technique that succeeds through brute force repetition and incremental improvement, rather than single-shot perfection. It's named after this naive Simpsons character who embodies try, fail, and try again persistence. I'll explain it in simple terms. It begins with a set of programming specs. An agent attempts to create the required code and runs it to produce a form of output. Then it confirms whether the goals were met. If not, the reason for failure informs the next attempt. And this loop tries again and again until it passes the test or runs out of retries. Generators can produce code that crashes, so error messages are also fed back for self-correction. I wanted to use this method to create visualizations rather than typical app code. I'll demo issues I've encountered when bots generate Python visuals. I'll create a prompt like this, asking for a combo bar chart and table. The data spans 5 years, across 5 categories, and I provide a list of counts. The bot uses default attribute settings to generate a visual like this. The first thing I don't like is that the legend and table category order doesn't match the stack order. The middle column header is centered under its bar, but the other headers are not. As someone who dislikes chart junk, I see unnecessary elements, like this border, the chart's y-axis, the table's full grid, and the chart legend. If I made this visual myself, it would look like this. To challenge the code generator, I'll request some very specific features. Numbers need to be flush right, but also centered under their bar. The top of the title needs to be level with the highest bar and flush left with the row labels. So this will be the reference image the code generator must try to replicate. But how can my loop auto-compare a generated visual to my reference? I drew inspiration from metrics that quantify differences between a reference image and a copy generated using a lossy compression. We can't compute metrics from raw images, but since each pixel has 3 color channels, we can represent them as 3D arrays. I used 2 metrics to compare image arrays. With the first one, lower values indicate less variance, and with the second, higher values signify lower distortion. So just like how we can compare a high-resolution original to a low-resolution copy with these 2 metrics, we can automatically compare a generated visual to our reference. But we also need a way to provide feedback about where improvement is needed most. With this formula, we can compute a difference map and divide it into sections to see which part has more mismatches. If we compare this reference to this version, we can see that the table's text formatting is off. For this demo, I'll highlight the generated version's headers and counts. When I display the difference map, we can see that the table needs to be improved. This overlay shows that the map includes the part of both images that differ. Here's another example to compare to our reference. I'll highlight the bars so we can see where they're located on the map. This version's bars are too wide, and there's no bolding in the table. The map shows variation in both the chart and the table, but we can see that the generated bar width creates the biggest difference. With a strategy for automated testing and feedback in place, I could now create a loop. In his original post, the inventor of the loop used a bash script, but I'm a Python guy. The code generator receives a prompt describing the data, chart, and table. A program is created and executed. The generated image is compared to our reference, and the reason why the new image wasn't similar enough is fed back to begin the next loop. Of course, if the code throws an error, that message is sent as feedback. The loop stops when the image meets our metric thresholds or when max tries is reached. Now we'll take a quick look at the comparison logic, which is also a Python program. The generated image is resized if its dimensions don't match our reference. The images are converted into 3D arrays of RGB pixel values. The peak signal-to-noise ratio and the normalized root mean square error are calculated. If the metrics are within tolerance, then the word pass is returned. Otherwise, it computes the mean absolute difference and returns the metrics plus the location of the largest mismatch. Finally, we'll see how my loop got incrementally better at producing visuals. The first attempts were not very good, with missing data, tables overlapping charts, and overly wide bars. Once the overlapping was fixed, missing data and font size were still issues. The biggest challenge was lining up columns with bars and obeying the text formatting specs. Right aligning was easier than centering numbers under bars. This alignment was close, but the rows are squished together. And here's the best generated visual, which was close enough to our reference image. So that's how I employed the Ralph Wiggum Loop to build better visuals. Rather than a human in the loop babysitting the process and validating generated code, the tool functioned independently until the goal was achieved.